everyone. Welcome to episode number 589 of this here electronic engineering podcast called Amelia's Weekly Fish Fry, brought to you by eejournal.com and written, produced, and hosted by me, Amelia Dalton. Are you powered up for today's fish fry? I certainly hope so, because my guest is Frank Heidemann from National Instruments, and we're diving into the world of power semiconductors. We chat about recent trends in the power semi space, the benefits of wide bandgap power semiconductors, and the role that these semiconductors will play for the future of electric vehicles. Also this week, I check out a new way to recover rare earth elements needed for green energy applications. Spoiler alert, it involves eggshells. But first, please welcome Frank to Fish Fry. Hi, Frank. Thank you so much for joining me.
Absolutely. Thank you for having me here.
Absolutely. Okay, so we're talking about power semiconductors today. But first, Frank, can you set the stage for us? When it comes to the future of electric vehicles, sustainability, and the EV market as a whole, what role do you see power semiconductors playing here, now and in the future?
I always say that power semiconductor is probably the only technology that really can save the world and change the climate crisis. And that sounds a little weird, but it is really true, because any energy we transform from A to B, we bring from one place to another, we generate and then use, always power electronics is involved. And when we think about like next year in 2025, we have probably around 76 million electrical cars in the world. And they're consuming roughly 300 terawatt hours of electrical energy. And if we are able to increase the efficiency by 3% due to power semiconductors, that is probably the amount of energy Germany consumes in one single year. So power semiconductor, in terms of sustainability and really changing something, is really a big thing.
So, Frank, what kind of trends are you seeing in power semiconductors in particular these days?
Well, power semiconductors, when I was young in university, we had silicon and IGBTs, and our professors told us that wide bandgap technologies like silicon carbide will be the future. And then I told my students that silicon carbide and wide bandgap will be the future. And then a couple of decades needed to get the first products out. And that was in 2001, first silicon carbide device from Infineon. And this trend, and it was actually a disaster, but this trend is going on. So wide bandgap devices, silicon carbide right now, where we have the most recent products and kind of newest technology for highest efficiency, best frequencies, best switching frequencies, best thermal conductiveness, which are really changing like the power semiconductor and power electronic world. And right behind gallium nitride, which is much cheaper than silicon carbide to produce, we have some other like architectural and technical problems with gallium nitride to make use of them in the automotive world. But these are the mega trends in the power semiconductor world right now, where we see wide bandgap really, really playing a big role now.
So speaking of that, wide bandgap power semiconductors are definitely a hot topic these days. But Frank, what do you see are the biggest benefits of these kind of ICs?
Wide bandgap devices, or in general, built on wide bandgap and compound semiconductors, they bring along a lot of benefits. So we can switch 4 times faster than silicon. We have a quarter of the size of the device, so we can shrink devices dramatically. We have much better thermal conductivity. So this is like the losses we produce, especially in power semiconductors, the losses we are producing, they are much easier to handle in the applications. And as I said, the higher switching frequency really reduce size and weight of the complete systems. So wide bandgap technology, especially in power semiconductors, are really changing the complete architecture and the way how we build inverters and transferring energy from A to B. But that's not only in automotive and transportation world. Also, gallium nitride for RF applications really, really changing a lot. So gallium nitride as power amplifiers for high frequency applications, they are so much better than we've seen it in the past, that it is really an amazing step forward what wide bandgap does right now for the technology in power semiconductor and RF technologies.
So when we talk about wide bandgap ICs, whether it's silicon carbide or GaN, we also need to talk about reliability testing as well, right? Can you talk about that a bit?
As always with new technology. So if you look at it, the world looks like technical innovation is always better. It's always the best, right? Like silicon carbide is so much better than silicon in basically all factors. But as it is, if you have a disruptive technology and a new technology, it's not always that anything is better. You have new problems. New technology has their burdens to carry on, and this carries out in reliability. So silicon carbide, it is massively reliable. I'm not saying it's not reliable, but we have different failure modes. So when we had decades of experience with silicon and IGBTs and really knew exactly what we needed to do of testing to identify the failure models and trigger the failure models, that changed with silicon carbide a bit, right? We have new failure models because of the smaller distances, the smaller dimensions, the higher frequencies, and especially the high DVDTs. So the time they need to switch is so much faster that this really changes something. For example, one effect is called gate drifting. So we have a dynamic gate drift effect on silicon carbide, which we haven't seen on silicon. So over time in a normal application, silicon carbide intends to drift to become a little less efficient over time. And these are normal applications. So this is just one example where we need new technologies in test as well, where we dynamically test these devices and prove that they don't have these drift effects dynamically on the gate.
That makes sense. Now, there is also a need for new dynamic tests in this arena as well, right?
Absolutely. This is one of them. And there are others. Like we have these physical effects that the material and the devices getting smaller and smaller because of the silicon carbide behavior. They can switch faster. They have better thermal conductivity, and we can build smaller devices. And at the same time, they're switching faster. So we have higher DVDTs. And it's not only related to the gate, it's also to the chip border. So there are failures in the field where we see breaking devices in like normal applications under high temperature and high humidity. And we cannot reproduce these failures with normal static tests in reliability schemes. So we needed a new test, which is called dynamic H3TB. And this is a dynamic test where we really stress the device under normal conditions, like in the applications. So very narrow application, narrow test. And we generate very high DVDTs to really trigger these failure effects at the chip border and prove that the designs of these chips are good enough to have these tests or have these devices in the automotive world. With that, it's not only that it is dynamic, it's also more challenging. So these tests are really technical, very challenging, and also not very cheap. So it is both. It's a financial challenge, but it's most of it a technical challenge to get these tests really proper done and put these tests in a form that we can really reference to some standards out there in the world.
So, Frank, there is also an evolution within the qualification standards for power semiconductors as well. So, talk to me about that and the role that NI is playing here.
Actually, silicon carbide or the driver for silicon carbide devices is really obvious automotive because they really gaining for higher efficiency and longer distances to drive. But also, on the other hand, they have much higher qualification standards and requirements as usually. So over time, the automotive industry sit together and developed their own standard, like a supplier standard. And this supplier standard, it's called today AQG 324, became a general standard which got overtaken by the European Cluster for Power Electronics. And now the complete community of semiconductor companies and test companies really developing these standards to new technologies like gallium nitride and silicon carbide. And what it really does, it gives a guidance for the complete automotive world and the electronics and power electronics in the automotive world, how to qualify a product, a silicon carbide product or a silicon product to be used in an automotive world. So this is kind of a very shortcut. It took over easily 10 years to get that standard to the point where we have really acceptance worldwide, and it is worldwidely accepted now. And NI, as very important factor in the world for testing, plays here a role. So I'm one of the co-chairs of the AQG 324, and we really help to develop that standard and get it as good as it gets to the point where we can really help to improve the quality of these devices for the automotive world. And this is only a automotive standard. And at the same time, we are part of the JEDEC, which is one of the most important standardization bodies in the US, and as well work on these standards for wide bandgap devices to get them as good as we can out there and help the semiconductor and power electronic world to rely on these standards and qualify their devices and make sure these devices can survive a car life.
Excellent. All right. Before I let you go, Frank, it is time for your off-the-cuff question. So if you could have one meal right now, it doesn't matter if it's on the other side of the world, you need a passport to get there, what would you have?
So many meals out there in the world, but I think it would be fish and chips in Edinburgh on Bronzeville Place. There's a place called, I'm not sure if I remember right, it's called Salt Water, I think. And that's probably the best fish and chips you can get. So I lived there for a while, studied in Edinburgh, and fish and chips is my favorite.
I love that. That sounds wonderful. Well, Frank, this was super cool. Thank you so much for joining me.
Thank you so much. Yeah.
What do eggshells have to do with rare earth elements? Well, apparently quite a lot. Check this out. A team of researchers from Trinity College Dublin School of Natural Sciences and ICRAG, the Science Foundation Ireland Research Centre in Applied Geosciences, recently discovered that eggshell waste could recover rare earth elements, or REEs, from water, providing a potentially environmentally friendly method for their extraction. Okay, let's step back a second. So, REEs are essential to a variety of green technologies, including wind turbines and electric cars, but are in relatively short supply. And ironically, extracting them from the environment can be very harmful to the earth. But this team found that calcium carbonate, or calcite, in eggshells can effectively absorb and separate these valuable REEs from water. So, this is how they did it. This team first placed eggshells in solutions that contained REEs at various temperatures, from 25 degrees Celsius to 205 degrees Celsius, over a time span of about 3 months. And what they found was really interesting. They discovered that the elements could enter the eggshells via diffusion along the calcite boundaries and organic matrix, and at higher temperatures, that the rare earth elements actually built their minerals on the eggshell surface. At 90 degrees Celsius, the eggshell surface helped recover formations of a rare earth compound called cozoite. As things got hotter, the eggshells actually underwent a complete transformation, with the calcite cells dissolving and being replaced by polycrystalline cozoite. And at the highest temperature of 205 degrees Celsius, this mineral gradually transitioned into bastnasite, which is a stable rare earth carbonate material that is used to extract REEs for technology applications. All of this suggests that eggshells could be repurposed as a eco-friendly, low-cost material to help meet the growing need for REEs, since eggshells do seem to trap distinct rare earth materials in their structure over time. Lead author Dr. Remy Rateau addresses the significance of their research like this. This study presents a potential innovative use of waste material that not only offers a sustainable solution to the problem of rare earth element recovery, but also aligns with the principles of circular economy and waste valorization. But the implications of this research could go much farther. Principal investigator Dr. Juan Diego Rodriguez Blanco emphasizes the broader benefits of the findings like this. By transforming eggshell waste into a valuable resource for rare earth recovery, we address critical environmental concerns associated with traditional extraction methods and contribute to the development of greener technologies. Super cool, right? So if you want any more information about this study or more information about NI's Power Semiconductor Reliability Test, I've included a couple links below the player on this week's Fish Frying page on eejournal.com and in the description for this week's YouTube episode as well. Hey, have you checked out EE Journal on social media yet? Well, you should. You can find us at facebook.com/EEJournal. If you're into X, you can monitor our tweets at EEJournalTFM. And don't forget, if you would like to follow my personal account, check out Amelia D. 1978. And hey, if LinkedIn is more your thing, I dig it. You can follow us or me on LinkedIn as well. And we are now on Blue Sky Social and Mastodon too. And we have a YouTube channel, youtube.com/EEJournal. Folks, it is chock full of all kinds of techie videos, including our very popular Chalk Talk webcast series, hosted by me. And of course, you can subscribe to our EE Journal YouTube channel as well. Also, make sure that you subscribe to this here podcast on Spotify, Podbean, Apple Podcasts, YouTube, or just about any other podcasting platform to listen to some exciting upcoming episodes. Thank you everyone for tuning in. If you know of any cool new technology or heck, if you just want to chat, shoot me a line at Amelia, that's AMELIA, at eejournal.com, or post a comment on our forums on EE Journal. For the week of June 28th, 2024, I'm Amelia Dalton, and you've been fried.